Okay, recording is started. So, hello students. This is a class of geotechnical engineering. So, till now we have discussed about different index property, and from previous class we have discussed about consistency of soil. Okay, so we're going to again continue from the last class. Fine. So, allow me to share my screen first. My screen is visual, right? Yes or no? Okay. So we are discussing about consistency limit of soil. Okay. So in the last class, we already discussed about the background of consistency of soil. Who have proposed this? This A. Atterberg. Okay, Albert Atterberg in 1911. He proposed this concept of consistency of soil, and it is specially it's a property only specially used for fine grained soil. Okay, and we have discussed about this variation curve, volume, the change in volume with changes in water content in a particular fine grained soil, and a soil may attain four stage of consistency, that is solid, semi-solid, plastic, and liquid. And here we already discussed about there are three limit. Okay, limit of water contents exist. Okay, that is liquid limit, plastic limit, and shrinkage limit. Fine. So in the last class we discussed about the liquid limit and plastic limit. Fine. And you can also go to the student portal for the laboratory test to determine liquid limit of soil. Okay, and also to find out how to find out plastic limit of soil in laboratory. Okay, all the details, all the standard procedure and reference video link all are given in your student portal. Please go through the particular video and the standard manual. Okay, and go through it. If you can't understand, you can get back to me, you can message me, and I'll explain to you. Okay, but first you have to go to your student portal, go through the video link, and also through the standard manual how to find out liquid limit of soil, also how to find out plastic limit of soil. Okay, now today we'll discuss about shrinkage limit of soil. Fine. So here the details of liquid limit of soil, it is already discussed in the last class. So it is the plastic limit. Now we'll discuss about shrinkage limit. Fine. So uh, it is it can also be explained from this sorry, from this diagram only. Okay, just hang on a second. Okay, so from this diagram we can also give a definition of shrinkage limit. Okay, now just seeing that shrinkage limit is what? It is the boundary water limit. You can see here again. Okay, it is a boundary water limit between solid and semi-solid state of consistency of soil. Okay, so we can say the definition of shrinkage limit, uh, what? It is the water content corresponding to an arbitrary limit between semi-solid and solid state of consistency of soil. Okay, just like the previous limit, that is plastic limit and liquid limit, we can also give the almost similar definition for shrinkage limit, only it is between solid and semi-solid state of consistency of soil. Okay, so let's go back, let's find out the alternate definition for shrinkage limit. Okay, so it is also this water content, or this shrinkage limit can also be defined as the maximum water content. It is defined as the maximum water content at which a reduction in water content will not cause a decrease in volume of soil, decrease in volume of soil mass. Okay, please mark in the statement. Okay, ध्यान से सुनो. I'm again repeating. It is defined as the shrinkage limit. Okay, it is defined as the maximum water content It is defined as the maximum water content at which a reduction in water content will not cause a decrease in volume of soil mass. That means it is that water content at which if you still reduce the water content, that means if you reduce the water content from this point, it will not result in the changes in volume. Here you can see this variation curve. After this shrinkage limit point, it goes horizontal. Okay, somebody is waiting in the lobby. Wait. Okay, after this point, what happened? Okay, so after this point, if you are still in decreasing the water content, the volume will remain constant. It will not going to further decrease. If it goes decrease, then it will go like this linearly up to this point. Okay, but it is not like that. After this point, it go horizontally to that y-axis. Okay, from where you can understand the volume of soil mass, it become constant after this point. Okay, in alternate way, you can also say that like that. You can also say like that. So if you suppose a dry soil mass you have taken at this point water content is zero. Okay, since water content is zero, that means what? Your soil is dry soil. Okay, for a particular dry soil, it must have some volume. Suppose this much of volume it has, and voids may be filled with air. Okay, because there is no water, there must be some void, and voids are filled with air only because there is no water. Fine. Now if you try to increase some amount of if you try to add some amount of water in a particular dry soil. Okay, suppose this amount of water we have added. Okay, just little. Then what will happen? Some void space may be filled up with water, and other voids will be filled with air only. Okay, that means what is the difference between that two cases? At this point, that the previous one, that is at this water content equal to 0 point. At this point, the soil is dry. Okay, that means the soil, if you consider the phase diagram, if you can imagine the phase diagram, at this point the soil will be in a two-phase system. That means the soil will have a solid and air only, since the soil is dry. Now if you add some amount of water, suppose this amount of water, okay, this amount of water we have added, that means what will happen? The soil become in a three-phase system. That means the soil mass will contain soil solid, of course. Then the voids will partially fill with air and partially fill with water. Okay, that means the soil is in partially saturated state. Fine. Now again at that position, there is no change in volume. Okay, because the volume of voids remain constant here. Okay, only the spaces that the voids are the place of the voids are replaced by water. Okay, before it was taken by the air. Fine. Now again, if you can increase this amount of water, little bit amount of water, same condition will occur. The soil will be in a three phase system. Soil mass contains soil solid, water and air, and the volume will not increase or decrease. It will remain constant here. Okay, so at this point, even at this point here you can say the soil is now fully saturated at this point, because at this point, that means if you add this amount of water in a particular soil, at this point the whole voids will be filled up with water. Again, this at this point you can say the soil is again become two-phase system of saturated state. Okay, that means the soil mass will contain soil solid and water. Fine. So I can repeat here. At this point, the soil is two-phase system of dry soil. Then this zone is called partially saturated soil. Okay, or partially saturated zone. And at the shrinkage limit point, the soil becomes saturated, fully saturated, and the voids filled up with water, whole water. Fine. Now there is no space for there is no space for water anymore now at present, because all whole voids are filled up with water now. Okay. Now after this point, if you again try to increase the water, I'm talking about fine grained soil only. Okay, this is a special characteristic of fine grained soil. They can increase their volume and they can also can reduce their volume. Okay, based on the addition or subtraction of water. from the voids. Okay, now if you can increase the water beyond this shrinkage limit, then what will happen? To sustain this additional amount of water, the volume of soil will get increased. Actually, volume of voids get increased, not volume of solid. Volume of voids get increased. Okay, that to create more voids, and that voids may be filled up with the additional water. Then that means what? The voids, the volume of the soil will goes and increase like that. Okay, you can try to increase the water content. The volume will goes and increase because it can hold the water. Okay, so this is the basic scenario of fine grained soil. Fine. So here I can repeat the definition of shrinkage limit again. So it is defined as the maximum water content at which a reduction of water content will not cause a decrease in volume of soil mass. Okay, there is another definition. It is it is the lowest water content at which a soil can still be completely saturated. That means after this point, whole soil are saturated. Term is saturated. Okay, this is the minimum water content at which soil becomes saturated. Okay, after this, the all are saturated. This is the minimum point. Okay, if you just try to reduce a little bit amount of water after this point, the soil become partially saturated. Okay, only at this point and after this point, the soil is saturated, fully saturated. Understood? So, is there any doubt on shrinkage limit? You can write yes or no. Shrinkage limit समझ में आ गया ना? Okay, so these three, that is liquid limit, plastic limit, shrinkage limits, together they are known as consistency limit, and it can also be known as Atterberg limit. Fine. So this is all about your consistency limit of soil. But in addition, I want to add some. Yeah, wait. This is all about shrinkage limit. You can read it out. Fine. Always think we have already discussed. There's some significance. Before the significance, I want to add something. Okay, wait. Hang on. Okay. So some important parameters are there related to consistency limit, and you should know this term. That's why I want to give you some small information. Okay, just like yeah, now I want to discuss about consistency indices. Some parameters are there related to consistency index of fine grained soil. Okay, there are some important property you can say for fine grained soil, like plasticity index, okay, shrinkage index, then flow index, consistency index, okay, liquidity index, toughness index, density index. Okay, density index, it is not for fine grains soil, it is actually for coarse grain soil. Okay, it is by mistake here, but I will going to discuss about this one also. And some miscellaneous property like sensitivity and activity we're going to discuss now. Okay, very small thing, so have patience. Yeah, so here, so first parameter is plasticity index. Okay, so very simple. Mathematically you can find out plasticity index for a particular fine grain soil. If you can find out liquid limit of that fine grain soil and plastic limit of fine grain soil, then just subtract the plastic limit from the liquid limit, that is WL minus WP. By doing this, you can find out plasticity index, that is IP, denoted by IP. Okay, capital I suffix P. Okay, very simple to understand. How to find out plasticity index? WL minus WP, that is liquid limit minus plastic limit. Okay, try to remember this equation. Okay, in some exam, uh, it may ask. Okay, there's some particular range to find out whether the soil is what kind of plastic, whether it is non-plastic or low plastic, medium plastic, highly plastic or not. I think the about the plasticity we already discussed in the last class. What is the property about? This is a property of soil that can allow it to reform or deform in any shape. Okay, you already got this thing in the previous class. So these ranges are very important. Try to remember this tabular form. Okay, that is a range of plasticity index. If plasticity becomes zero, that you can say it's non-plastic, because that means the soil doesn't have any plasticity. If it is more than 17, then you can say it is a highly plastic soil. Okay, fine. So there's a range. Next, shrinkage limit. Okay, similarly, like plasticity index, we have to discuss, sorry, shrinkage index. Okay, denoted by is. Fine. So how can you find out is? It is defined by the plastic limit minus your shrinkage limit. Simple. Okay, just on almost similar. Okay, plasticity index is defined as what? Difference between liquid limit and plastic limit, and shrinkage index is defined as the difference between plastic limit and shrinkage limit. Fine. You just go through this statement. Next, flow index. I better advise you to first go through the laboratory test to find out liquid limit of soil by Casagrande method. Okay, it is already available in your student portal. You can go through the video link. First, go through this that particular video. In that particular experiment, liquid limit experiment by Casagrande test, there's a curve you need to prepare. Okay, in that curve, the slope of the curve is known as flow index. Okay, so you maybe get confused here how to find out flow index. First, I just want to advise you, first go to the liquid limit test, how to find out, how to determine liquid limit in laboratory by Casagrande method. Okay, you will get the information about flow index. Okay, after that you will come here, you just find out the about definition of flow index. Okay, anyway, I just want to read it out. So flow index, it is the slope of flow curve. It is the slope of the flow curve obtained between numbers of flow and water content in Casagrande test for the determination of liquid limit. Okay, so I advise you first go and try to understand this Casagrande test for determination of liquid limit. Fine. Flow index indicates the loss of strength, shear strength of soil upon the increase of water. Okay, and it is defined by this equation: IF is equal to W1 minus W2 log of N2 minus N2 by N1. N represents numbers of blow. And what is numbers of blow? You will get the information in that particular experiment. Okay, that is your determination of liquid limit by Casagrande method. Okay, so don't worry about that. First, go through that video. Fine. And next, consistency index denoted by IC. Okay, and particularly you can find out consistency index by this formula. These are only some relation. Okay, consistency index, that is denoted by IC. How can you find out? Liquid limit minus natural water content divided by plasticity index. Now, what is plasticity index? That already we have discussed here. This one, plasticity index, IP. How can you find a plasticity index? WL minus WP. Fine. So consistency index can be defined or can be determined by this relation: liquid limit minus natural water content. Natural water content means whatever we have soil taken in your from the ground or from the field, just take the water content. That water content will be your natural water content. Okay, so liquid limit minus natural water content divided by plasticity index, you will get consistency index of soil. Fine. Okay, and there's some tabular format for defining what type of consistency of soil is there. Okay, we'll just go through this. Okay, then it is liquidity index. It is similar to consistency index denoted by I suffix L. Okay, not IL. L should be in a suffix. Okay, so how can you find out this liquidity index? Almost similar to consistency index, just you can see here in liquidity index you can find out by your see natural water content minus plasticity index, sorry, natural water content minus plastic limit divided by plasticity index. Okay, and there is a relation between consistency index and liquidity index by this: liquidity index minus, sorry, equal to 1 minus IC. That means whatever value we have got in consistency index, just subtract from 1, you will get liquidity index. Okay, it's very easy to understand. Similarly, another one is their toughness index. Okay, again, to find out to understand this toughness index, you need to understand this flow index. Okay, now to understand this flow index, you have to understand this Casagrande liquid limit test. Okay, and first you go through this test, you will find out this flow index. After getting this idea about flow index, you can find out toughness index. Why? Because toughness index is defined as the ratio of what? Plasticity index divided by flow index. Okay, fine. Now anything else? Yeah, this density index. Okay, now first of all I want to tell you density index, it is not a basic property of this is not used for coarse fine grain soil. Mainly it is used for coarse grain soil. Okay, and it is what it actually you need to understand this relation. You have to remember this relation. Okay, now density index, we already discussed about this density index. It is also considered as one of the index property of soil. Fine, and it is usually used for coarse grain soil. Fine. Now, what is this? It is defined as the ratio of the difference between void ratio of cohesionless soil in the loosest state and the void ratio in its natural state to the difference between its void ratio in the loosest and densest state. It's look very long definition, but if you can remember this definition, this statement will come very easily. Okay, now you can see ID, which is representation of the density index. Okay, I suffix D. It's a relation. Okay, it's a relation of what? It's a ratio. E represent void ratio. Fine. And max represent maximum. MIN represent minimum, and it is natural. That means maximum void ratio minus natural void ratio to the maximum void ratio minus minimum void ratio multiplied by 100. It is expressed in percentage. Now, what type of soil have maximum what, and in what case a soil may have a maximum void ratio, and in what case the soil may have a minimum void ratio? It is when a soil is in a loose state. When a soil is in loose state means what? The soil particles are too far from each other. Okay, they are loose means what? They are not close to each other. In case of dense state means what? Whenever you understand, whenever you heard this term dense state, dense state means what? In that case, the soil particles are so close to each other. Okay, the volume of voids will be very less. Okay, in case of loose state, the particles are far from each other. Okay, that means the void will be high. Okay, try to visualize that particular concept. Okay, in case of loose state, the soil will have maximum void ratio. Okay, that means in case of loose state, soil will have E maximum. In case of dense state, soil will have E minimum. Because in case of dense state, soil particles are so close to each other that means the voids are very small. The gap between the voids will be gap between the particles will be very small. Okay, so from this it is, you can find out using this relation, you can find out density index, and this is a property of coarse grain soil. Okay, or you can say cohesion less soil. Fine. Okay, this is all about the basics property of fine grain soil for related to consistency index. They are plasticity index, shrinkage index, flow index, consistency index, and liquidity index, and also toughness index. But density index, it is not related to your consistency index. It is related to your only for cohesionless soil. Fine. Now we'll discuss some miscellaneous property. Only we need to go for some basic introduction of that. Okay. So I will not go in depth. Okay. So you have to aware of this. The sensitivity and activity, they are the property of fine grained soil. First of all. Okay. And this is a relation. In this relation usually come in exam. Okay. It is defined as a ratio of unconfined compressive strength of an undisturbed soil sample to the unconfined compressive strength of the same soil after remolding at alternate water content. Okay, here very much unknown terms are there. Unconfined compressive strength. Okay, undisturbed sample. Okay, this term will be introduced to you in few coming classes. Okay, I think strand, about shear strand, this shear strand of soil, I think this term will be discussed by Chinimuni ma'am, maybe not, maybe in coming classes. So I don't want to be discussed here now because you will get confused here. Okay, for now only try to remember here the ratio. So sensitivity of soil is denoted by ST, and it is a ratio. That is it is a ratio of unconfined compressive strength denoted by QU, undisturbed soil by the remolded soil. Okay, remolded or disturbed soil, whatever you say. Fine. Next, activity. Activity also a kind of a property of fine grained soil, especially for clay soil. Fine. Now it actually represents how much percentage of clay soil present in your particular fine grained soil. Okay. Now, activity is defined as what? It is a ratio of plasticity index of the soil to the percentage finer fraction available in the soil particular. Okay, so we can, in this relation, you can, in this definition or in this particular expression, you will understand activity and denoted by AC. Okay, small AC, it is not here, you can also write down here small a suffix c, AC. Activity is defined as the ratio of plasticity index, you can see plasticity index, and the percentage finer or weight of the soil finer than 2 micron or 0.002 millimeter ISC. That means the amount of clay present in a particular soil. Okay, the ratio of IP and the percentage of fine grained soil finer than 2 micron. This ratio will give you activity. Okay, now this is a very basic important thing to remember this, that this tabular chart. That means if particular fine grained soil, if your activity, that means this ratio is become less than 0.75, that means you can say it is inactive. Okay, that means the fine or clay soil is have very less amount. Okay, now if the soil have more than 1.25 activity or 1.25 of activity, then we can say the soil is very active. Okay, that means the soil may contain higher amount of clay soil, or it may exhibit the property of clay soil. Okay, so these are some miscellaneous property of clay soil. Okay, so yeah, this is all about today class. Is there any doubt? You can ask me now. Anything to ask?
No, sir.
Okay, okay, good then. So I'll just close my sharing now. Okay, wait, let me stop my recording.